All right, hello. How you guys doing? I almost every semester I teach at noon. This class, at least once a year, and it's always at noon. So I'm always like, do I say good morning or good afternoon or? And I guess it's technically afternoon every time. So good day. um, all right, so I think you should have, if you checked, you should have seen these slides in Moodle. The previous slides up. So this is going to be what I'm aiming to do for you, is to have these up if you wanted to take your own notes as you go on some device or just follow along, and then later post my copy as well for you there, and just kind of replace the blank one. All right, I did have somebody approach me with interest in moving the exam one by a class period to avoid some other conflict. I forgot to set up a poll for that, so I'll try to do so on Tuesday and get your feedback. If I pull up the syllabus, we can check and see. I do have a slot where we can flip it, but certainly I wouldn't want to do that if everybody else has an exam on the other time period. So I'll pull that up real quick so we can take a look, and then you can think until Tuesday to see if that would actually be reasonable, and if most of you want it to be changed, I'm happy to change that. Okay, so get this for you here. So the dates potentially could be, let's see. I think it would be pretty easy to move it back by one period. If it was, actually, I'm not even sure. Was it exam one or two that two, exam number 2. Okay, that's actually even a little easier. So the Flint water crisis here, I do not mind providing after exam 2. So if you'd rather have the exam on Halloween, I can make it nice and scary for you. I can certainly do that, but I'm going to get your feedback on Tuesday. So check your schedules if you haven't. Sounds like, at least for some of you, maybe that's an exciting possibility aside from the Halloween situation. So give that some thought. That's the easiest potential thing to do for us there. All right. Anything else logistics-wise? Any questions, concerns? Would a change like that be a relief to a lot of you? Okay, a few vocals. Some people don't care. Maybe some people care a lot, but okay. So I'll plan to set up one of those live polls again on Tuesday to get your feedback there. All right. So today I'd like to dive into kind of the nuts and bolts of how we go about environmental engineering, right? And about these systems. So specifically units and mass balances. So most of the units part should be just review for you, I hope. But perhaps you haven't seen some of these units or thought about what is kilo versus milli versus centi in a while. So we'll talk about a few basics. I'll lay out a few expectations. Perhaps most of you don't remember, or maybe never learned, that there are 1,000 liters in 1 cubic meter, right? For example. So if we're talking about water, we're talking about flow rates. There's a few things like that I'd like to have for you to have in mind so that you could do that conversion without too much stress. So we'll talk about some of that. In general, if you are paying good attention to your units along the way, and this applies, by the way, for more than just my class, but for most engineering in general, it will serve you well because you will have a guide to understand where you're going, even if you forgot what you're doing. Okay, so especially as you have this formula sheet I'll give you, but if you know the pieces and know what their units are, that makes everything a lot simpler. And you can always take a look at your final answer and say, well, what are the units I calculated, and does that make sense? Did I ask you for years and you're giving me kilograms? Maybe something went wrong, right? So it's a very good practice. in this class especially, but I think probably all of your technical classes. Okay, so given that, and given the fact that conservation of mass is quite important and essential, we will be able to solve a variety of problems just on the basis of those two things. We're going to have continuity between, as we'll walk through different units, and we're going to set up mass balances based on typically changes in mass over time. Sometimes it'll be number, so maybe we'll do numbers of bacteria or something. But in general, changes over time, that's our basic principle. So we might have some rate at which something's happening compared, so maybe rate of production of something compared to a rate of destruction of that something. And we could find a balance. Maybe simply, rather than a rate of production, maybe it's coming into our wastewater treatment plant at some rate. We'll make some assumptions and make it a little simpler and say that's a constant input. Then we have a rate at which we're transforming it to get rid of it. And we can find ultimately some steady state balance of how well is our continuous flow system doing at treating this waste. Okay, that's the type of thinking we're going to develop, and using these rates in mass per time units. So very often we will use this in some sort of flow rate. So Q being a flow rate of water, that's the term we will use. Now, we're not typically tracking just the water, it's usually something in the water. So like we said last time, we will have some concentration, maybe C as a concentration of some pollutant in that water, let's say. And if we multiply concentration by the flow rate, it's a good example of units already. If we just take Q times C, I'm going to do it up here. So Q times C will give us a flow rate is some volume over time, right? A volume that's flowing, how fast is that flowing? So that'll be volume over time, multiplied by the concentration, which will typically be mass or maybe moles per volume. Okay, so that ends up giving us a mass per time, if I write it all out very explicitly, because the volumes will cancel. So that's one way to get a rate, a mass rate of change over time. Or perhaps we just say we're adding 10 kilograms a minute. That would just be mass over time. That's also fine as a rate. So it doesn't really matter what kind of form we put it in. We're going to be dealing with mass over time almost always for many of these things. So when we talk about the mass balance, that's the type of dynamic that we're looking at to balance. Okay, I know that a fair bit of you were not so comfortable with chemistry, and this lecture and the next one should assuage your fears a bit and say, look, it's not that bad, especially if we just treat it like units. Okay, so we're going to touch on the chemistry units today. The next class we'll dive into, okay, well, how do we do some of this chemistry? A bit of a refresher. So we'll touch on it today, but really it's a matter of units. So you can do it. You don't need advanced organic chemistry or inorganic chemistry, or even the advanced levels of general chemistry. You really don't need that level of chemistry for what we're going to do. We just need a few tools from it, and we need to be able to track our units. Okay? If you can do that, you'll be fine. So hopefully I'll help you prepare for that and refresh you on that. Chemical equilibria, that's the one topic, the one particular tool that we will have to use for a few things. And like I said, I'll give you some refresher on that, especially for next time. Okay, so on to units. My expectations are that you're pretty good with the SI units in general and the conversions for things like a kilogram is 1,000 grams, right? A kilometer is 1,000 meters, right? Some of those are pretty obvious. I hope that you kind of are familiar that there are some other ones. For example, nano, you might see. We use that sometimes, nanograms per liter of something. It's a little less common. Things you really want to know would be milli, micro. Centi is probably good, and you probably know that from like centimeter, and kilo. Right? Of course, these are prefixes that could apply to a lot of different systems. So I hope that you are familiar with that, have no problems with that. Take a look, study that if you need to. Now, on units and on lookup tables, this is the lookup table you're going to have on the exam. It's just what I have there. It's what I provide. That's on your formulas and tables. It's posted on Moodle. And I'm not trying to be sneaky about this because I'm telling you right now, but it is a little sneaky if you forget it on an exam. Okay? There are units in this table. The units are not after every single number. So you need to check the units for a category. For example, the dynamic viscosity units. You might forget and think that the units are just kilograms per meters per second, but actually this table is a little sneaky and includes that times 10 to the minus third. So inevitably, somebody's going to forget and do that wrong on an exam and be off by a factor of 1,000 for something. You'll be wrong. I tend to give partial credit if I can see you basically had everything right, but you forgot that. It's pretty obvious to me, but pay attention to your units. It will help, right? So even that would be part of the unit in that case. Units are there. Make sure to remember that one. All right, so a few that I'd like you to know. I already mentioned this one. How many liters in a cubic meter? 1,000. And you can visualize that. I often have my 1 liter water bottle here, and you might think that, okay, a meter is a little over 3 feet, maybe something like this. Cubic, right? How many of these might you fit in there if you stack them all in a row? Well, it's going to be a lot. And if you think about pouring those bottles of water in that cubic meter until you have it full, you're thinking at least hundreds of times, right? It's definitely not 10 liters. You can just visually see that, I hope. So that's 1,000. You should then also be able to know, okay, how many milliliters in 1 centimeter? If you do the calculation, and this is actually a good one to go through for unit conversions, there's 1 milliliter in 1 centimeter. Now that might strike your sensibilities a little funny, right? Because 1 milli is 1 times 10 to the minus third, so 1/1000th, 0.001, we'll say, liters. But then centi is only 1/100th of a meter, right? So a centimeter is 0.01 meters. So at first, you're thinking to yourself, oh wait, this is really weird. Why is there such a difference here? Well, remember that if you're going to do a unit conversion like this and you have an exponent, capture the exponent within that conversion. So essentially what you would need to do is if you're going to convert from cubic meters to milliliter, you actually have to account for that cubic, right? So let's first do 1 centimeter cubed. Let's say 1 meter cubed is how many centimeter cubes, cubic centimeters. So we've got a question there. Well, we know that, and I'm just going to write this down here. We have 0.01 centimeters equals 1 meter. Now, if we cube it to do that conversion, we're going to cube all of that. We're going to cube all of both sides. So that would mean that we have 0.01 to the third power cubic centimeters for every 1 cubic meter, right? So 0.01 to the third cubic centimeters in 1 cubic meter. Now we cubed the 1 over here too, but 1 cubed is just 1, right? So that's the caveat there. So I'll put it for you to solve this part. How many grams are in 1 milliliter of water at 5 Celsius? So at 5 Celsius, if we take a look, we have our lookup table. Let me find my cursor. Right here, that's the mark. Right, 5 Celsius, our density is 1,000 kilograms per cubic meter. So I'm going to write that down on the next step. At 5 Celsius, our density and from there, you ought to be able to calculate how many grams in 1 milliliter. So take a moment and solve that. All right, so there's probably a couple ways or orders of operation you can do this in. The first thing that comes to my mind here is to say, well, we know there's 1,000 liters in a cubic meter, so we could convert the volume units to liters, just multiply by, well, 1 cubic meter for every 1,000 liters. So we're essentially dividing by 1,000 here, and we get 1 kilogram per 1 liter. Now, that's another factor that you can take and commit to your memory, that at least at 5 degrees Celsius, my water bottle is 1 kilogram without the bottle, right? So if this was a little bit colder, if I refrigerated it, and I had exactly a liter in there, it's 1 kilogram, which is about 2.2 pounds, right? So tangibly speaking, you could think to yourself, okay, how much does 1 full water bottle weigh? It's not going to be thousands of pounds, at least, right? Or thousands of kilograms. So we could start thinking about this in something that you can feel or relate to. And if you had, 0.001 grams for a liter, you're off, right? Because this is not like the weight of air. Okay, so that checks out. That sounds about right, and I'll just tell you right now, that's a useful thing to keep in mind, is at least at 5 Celsius, water in general, it doesn't change a whole lot. Density-wise, it changes a little, but so it's about a kilogram in a liter, almost always. So with that, then we could say, all right, well, let's convert grams from kilograms to grams, right? So this would be, that's 1,000 grams per liter. Well, let's then convert milligrams. Well, there are 1,000, given our units here, there are 1,000 milliliters in 1 liter. So this would just be the same as saying 1,000 grams in 1,000 milliliters. So that's 1 gram per milliliter. Another thing you could keep in mind if you wanted to, right? So if you've ever been in a chemistry lab or something and you use a little pipetter or of some sort and you get maybe a milliliter or a few milliliters, well, each time you're getting 1 milliliter, that's approximately 1 gram. And in fact, that's often how we can calibrate our weighing scales by taking a known amount of water at a known temperature and seeing how much is that scale weighing. We could calibrate our pipettes that way if we trust the scale, or maybe try check the calibration of the scale if we trust our pipettes. Okay, so that's just a hopefully complete review. Feels silly almost, but this is the kind of stuff that can trick you up and can get in the way of you solving a bigger problem. So I wanted to take a little bit of time just to make sure we have a lot of these pieces in order and are comfortable doing unit changes, right? Because a fair number of you are civil engineers who've probably done plenty of unit conversions in other scenarios that I would get tripped up on, and we're going to be doing this in the world of water and wastewater, okay? So it's going to just be a different flavor of stuff you know how to do. So speaking of, next up is moles. Now, how many of you that dislike chemistry get frustrated by moles? Okay, I have hopefully something of a solution for you. And it's silly and in a way that hopefully helps. Okay, when we think of a mole of something, it's a lot like saying a dozen of something. Okay, so a dozen eggs, you go to the store and buy a dozen eggs. You know what that means. That's a useful amount. It's 1 carton. You know what to do with it. You know how many batches of cookies you could make or loaves of bread or whatever, right? You know something about what a dozen is. It's 12. In fact, you could write a dozen as 1.2 times 10 to the 1 power of something. You've probably never ever done that in your life, but that is a dozen, right? That is one dozen of something. If we said 1.2 times 10 to the 1 eggs, that would be 1 dozen eggs, right? Never in your life have you done that. That's what we're doing with moles, okay? And so if we stop and think about when we're baking a cake, making a batch of cookies, or being a little nefarious and maybe egging somebody's car, didn't quite get there. Let's assume not. You're going to use a number of them because there's just a certain number that goes with the recipe, or whatever you're doing to your pranking your friend's car, we'll say. You're not going to do that by the weight of cookies you're making necessarily, or the weight of the car that is your target, right? You're doing that on a number basis. So I'll elaborate a little more, but just keep that in mind. It's just a number, right? A mole is a number in the same exact way. You're going to have a number of molecules reacting with some other number of molecules or atoms because it's the number that matters, not how heavy they are. All right? That's the deal. You would not compare a dozen eggs to a dozen grains of sugar in your formula for your cookies, right? That just doesn't make sense. Okay, so when we talk about concentrations, and we'll come back to the moles because usually we deal with that in concentration units. So really, the super not so technical way to say this is a concentration is some stuff in some other stuff. Now, If you want to go more advanced, I have a grad class on aquatic chemistry, and we went a little more advanced on some of these things this morning. So feel free to let me know. But the basics is we have some water, or maybe air or soil or something, typically water for us, and we have something in that water. Right? There's a certain amount of residual chlorine in this water, and we'd want to express that in some either mass or number, or sometimes volume in the other stuff. Right? So the mass of chlorine per liter in here should be something like 0.5 to 1.5 milligrams per liter. So there should be somewhere between 0.5 and maybe 1.5 by regulation, since I just filled this up. Maybe it's a little lower practically, but there ought to be that coming out of the water fountain of milligrams of free active chlorine in every liter. So there are a few ways we can describe concentrations. Depends on kind of what purpose we're using them for. So sometimes we will do volume. That's actually going to be a fairly common way. That'll be our denominator, right? So our per liter, per cubic meter, maybe a percentage by volume. We might do a mass, so a grams per gram. That's a little more common for like soils or kind of solid mixtures. So how many milligrams of this contaminant for every kilogram of soil that we're dealing with, for example. Sometimes we use parts per X, so parts per million, parts per thousand, parts per trillion, or billion. You'll see that as PPT or PPB, ppm. That's pretty common, and actually, even if you feel like you've never dealt with this before, you've dealt with this way before you came to college. The reason is because you've learned percentages. So parts per 100 is percent. That is simply what it means. That's some amount in 100 total, right? Some part per 100. That's a percent. So if you have 5 parts per 100, that's 5%. Okay? It really is as simple as that, but we just very rarely think to say, oh, parts per 1,000 or parts per million in the same way that we do with percentages. So that would mean 0.1% should be 1 parts per 1,000. Now, sometimes people will use PPT for parts per trillion. Usually if there's a capital T, it's parts per 1,000. Don't worry too much about it. If I'm dealing with that, giving you something like that, I would specify. And in fact, the parts per 1,000 can be denoted by the same percentage sign with an extra little zero there. That's kind of a convention there. If you look at percent, the Latin roots here are basically right there. So per and cent meaning 100, like a century kind of thing, right? Or 1 cent is 1/100th of a dollar. Okay, so that all can make a lot of sense. If you see it, just try to understand. Typically what we're going to talk about is some mass, usually a mass per volume. Sometimes they would do like a parts per million by volume. That means volume per volume. Don't worry too much about it. We're not really going to use it all that much. I just want to show you, hey, this is what it is. Here's how to deal with it if it did come up. Okay? All right. Of course, can be either volume or mass, but often it's mass. And if we're in water, that also kind of means it's basically volume. So in water cases, if we have 1 ppm, it turns out to be about 1 milligram per liter, because water is about 1 kilogram in 1 liter. So that's it all works out quite well. Okay, so back to moles. This is the example, right? So if we are describing some chemical species, so we're talking about the numerators now for the concentrations. we want to know either the mass or the number typically. For chemistry, we often have to compare on numbers because maybe we use 1 dozen eggs to egg 1 car. If we have 5 cars to egg, we know how many dozens of eggs to use, right? That's the chemistry analogy to say we need some number of reactions to occur. Therefore, we need some number of moles for that reaction to happen, or a comparative, right? Because we're not going to take 1 ton of eggs because the car weighs 1 ton. We're not going to do that, right? That would make no sense at all. And by the way, don't egg anybody's car. Probably ruins their paint. Obvious. Hopefully that would happen if you tried, right? But hopefully this also kind of sticks in your mind, right? There's a reason we use moles. It's just simply because, one piece has to react with another piece. It's not about their weight. So when we, as engineers, we want to use weight for something because it's a lot more convenient to weigh this and dump it in. That's great, but we have to also know, if we're going to do some calculation with it, that it's not the mass that's reacting with the mass. There's a number comparison involved, right? We could drag this analogy until it's, dead and say, well, maybe 1 egg for every window and handle, right? And then you have an exact number comparison because you wanted to accomplish something particular. It's not about the mass there. But of course, we have to use mass sometimes because that's what we weigh. So that's why in chemistry we go back and forth with this frustration between moles and mass, and we actually have to do both, okay? So there will be some of that in the class, but like I said before, it's just units, right? And think of it as a dozen, just a bigger number. You're not even going to need to remember that a dozen is 12 or that a mole is 6.02 times 10 to the 23rd. You don't need Avogadro's number. You just need to know that what we're doing is going from a mass to a numeric, a number of molecules. And that when we do chemical reactions, we have to deal on the number. That's what you need to remember. Okay. So, real quick about just that. The number, moles are that number basis. And the periodic table, you'll have one on all your exams. They have a number listed right here that corresponds to the atomic weight. So we can find the atomic weight of any molecule with multiple atoms. Let's say hydrogen gas, for example, would be about 2 grams per mole because there's 2 of them, right? And each one weighs about 1 gram every mole. This number here, that's indicating grams in every mole. So here we have a weight to number ratio. So maybe an egg weighs 100 grams or something, I don't know. You would say a small egg, a medium egg is 100 grams, and a large egg is 200 grams per dozen. That's kind of the comparison here, right? This is a mass per number of these. So just as a chicken egg is going to be different than a little robin egg in mass per dozen eggs, and a dozen ostrich eggs might even be hard to lift because they're so massive. Our atoms and molecules have the same way, right? There are different numbers, different weights corresponding to each atom. So the atomic weight here, that's just particular to each atom. That's something you can look up on the periodic table. And then we can use that as a simple conversion to say we have 2 moles of this per liter. That means we have X number of grams per liter. Okay, that's just what we're going to use to convert from the number of them to the mass of them. When we do need to work in concentration units for some sort of chemical reaction, then we need to make sure we're in molar units. That is moles per liter. Okay, so this will be the common piece that you need. So when you have these brackets for some molecule, right here, these brackets like this. So the brackets of X is the moles of X per liter. We do not use the brackets if we're talking milligrams or any other mass convention. So you might say there is 10 milligrams per liter of X, then we need some calculation to figure out how many moles per liter of X there is. Those are usually not the same. Okay. Make sense? Doing okay so far? Okay, we will spend a little more time on chemistry. This is sort of the units side of it. Okay, another topic that we will cover is disinfection. And oftentimes you'll even see this in kind of real world applications. Lysol, for example, might advertise, oh, it kills 99% of germs or 99.9% of germs. Well, that's kind of obvious to us of what that means, but when we're doing a disinfection experiment or analysis, we will look at some number concentration of those germs, usually a bacteria or a virus, in some volume of water. For example, I'm quite confident there are at least several million bacteria in my water. And I just drink it for emphasis, just because it's funny. Hopefully there's no pathogenic ones that are living and able to infect. Right? That's the difference, and we'll come to that later in the semester. But there are certainly some algae, some whatever came out of my saliva. It's been at least a few days since I've washed it, if not longer. There are living organisms in there. There's probably algae and probably viruses that infect algae. There's going to be a lot of stuff in there. So long as it's not infectious, I'm happy, right? So it's not going to give me a problem, I'm happy. So we might look at the number of germs in pretty large numbers because they're very small, and if you have a bunch of them, there can be hundreds, thousands, millions of a particular bacteria in water, in a liter or in a few milliliters. So we're working with big numbers, so a lot of times we end up using logarithms. So if we're saying 99% reduction, that means there's 0.01 remaining as a fraction. Oftentimes we'll describe these as, when we count them, the way we'll do that is spread them on a petri dish and see how many colonies pop up that correspond to a bacteria. We can do a similar thing with viruses, and then they're like plaque-forming units. So colony-forming units or plaque-forming units, you'll see these pretty often per liter. Sometimes you'll see a few per milliliter. You get the point. It's a number of cells or organisms per volume. So here's an example where we're using a number concentration instead of mass. It's actually, in that way, it's a little bit like moles, but we don't have to do any weird conversions to mass in this case. And that would be, we'll typically use the letter N for a number concentration instead of C for we would often use as a mass concentration or molar, just basically chemical concentration is more typical for C. Okay, I'm going to erase that because I'm worried that might be a little unclear. Just to let you know, I often use C for like a chemical and N for like the bacteria or virus kind of stuff. And that's pretty common, and the textbook does the same. Okay, so I'm just going to leave it like that to avoid any confusion. So as we compare concentrations, we want to know, did we disinfect enough? That's kind of the question, right? A lot of times we're designing a system to remove 99.9% or whatever. So our thresholds are often, let's eliminate this number, and then we'll be confident that any that happen to be remaining, there's just simply not enough to cause an infection. Okay, so that's oftentimes the framework. Again, we'll talk more about that when we get into disinfection studies in particular. So we're often comparing the N at some time T, or some final N, compared to the initial time that we started with. And what we want to see is that we've killed most of them, right? So if our final N, and I'll just leave it as N for now, n at some time later, the final n after disinfection. If this is, let's say, 0.01, that means there's 1% remaining, meaning 99% were removed or destroyed. Okay, so this is 1% remaining. And on a very technical term, we could say 1 minus n over n naught, which actually becomes a bit intuitive if you just stop and think about it for a minute. That's the fraction removed. So in this case, that would be 0.99, or if we express that as a percentage, 99%. So that means n over n naught literally means the number concentration remaining compared to what we started with. It's what we ended up with compared to what we started with. Okay? So hopefully that's pretty straightforward and obvious when you stop and think about it. It's not overly complicated. But then one thing we'll do when we describe something like this, especially if we go into like 99.99% or 999, so on, is we tend to just shorthand it and let's use a logarithm, right? And so for 99% reduction or 0.01, if we take log of 0.01, so log base 10, so 10 to the what power equals 0.01, that would be minus 2, right? So 10 to the minus 2 equals 0.01. So the way we freehand it then is we say this is a 2 log reduction. And the easy way to think about that is we move the decimal place over 2 times, right? So all of this comes together into be like, oh, that's stupidly simple. But I want to tell you it outright and up front because this is just common convention to say these things and to make sure you know where all of this is coming from. So this then is a 2 log reduction. And likewise, a 3 log reduction would be 0.001 remaining, which is a 99.9% reduction. So if we want to elaborate, we could go all the way up to a 6 log reduction or whatever. And that's just a little easier than writing 99.9999999% removal. Okay, so I think that I was a little ahead of myself. All that's written right here. So we could take the example we just already did. If n is 1, when we're doing that comparison of n over n naught, if this is 1 and 100, that's a 2 log removal because it's 1 over 100 equals 0.01. Now, there will be, so this is what we use for disinfection. There will be one category of in our course where we're going to do a little bit of the opposite. We're going to compare particle numbers as we're causing them to aggregate and accumulate into larger particles so that we can sediment them easier. And we're actually going to flip this and just say n naught over n. So how many of the original particles in every one of the final ones? So we'll now care about the final particles that have accumulated on the basis they've grown based on smaller particles. If n naught looks something like this, a bunch of particles in solution, and n looks like one larger particle made up of each of them, the n naught over n is a very similar way of working with this. It's not disinfection necessarily, but we will see this for a little while when we do some coagulation. So it's kind of the same concept. We don't really do the log stuff for this, but just letting you know, sometimes we will compare it with it flipped because it's meaningful to do so. Just, again, it depends on what we're looking for. And saying it all out is a good way to make sure that you're on, like, in a good understanding of the system. So for disinfection, we're almost always looking at how many did we end up with compared to what we started with. That's the basis of our comparison that we need. In a different world, when we're doing aggregation, we want to know how many of those initial ones built this larger one so we know how big the larger one is. Okay. Any questions or issues on all that? All right. Okay, so what is a mass balance? Now, some of you may have never heard of this. Some of you maybe you've seen a lot of it. And of course, we could look at different styles or types of mass balances. But in the context that we're going to deal with, I already said this, we're almost always going to look at some sort of accumulation rate. So the rate at which a mass, or sometimes number, is changing. So overall, we have something like the change in mass over time, and usually that's in some volume. So usually this will be, instead of mass, we'll say concentration. And then we would say, okay, the change in concentration in that volume. So our typical accumulation is we take a look at some reactor. In this case, we have the little circle as our reactor, and we can draw a line around it, say this is a control boundary, so anything that goes into or goes out of that is what we're interested in understanding, and anything that's happening inside there. We isolate it from the rest of the world, except for any inputs that are crossing that boundary or outputs that are leaving that boundary. And then we can track any of the pieces that are happening that change the mass or the concentration, either at the inputs and outputs or inside of it. So for a very simple scenario, we can say that if no reaction's happening, then what's going in is what's going out, right? It's very simple. If you have a pipe and then there's a little juncture box and a pipe leading out, what's going in is what's going out, unless there's some reaction happening. Likewise, we could have two pipes coming in, maybe different concentrations, so it's a little more complicated, but what's going in is still what's going out. Or you could have one pipe coming in and two pipes going out, right? Overall, the balance is there. There's the same amount of stuff going in over time as it's going out. The same thing can hold true if we have a reaction going, but it just might increase or decrease the amount of stuff in there. So an accumulation rate then is how we're going to develop a mass balance to say what is or is not accumulating in this system, in this box or circle. We're going to say that accumulation rate is going to be equal to any of the inputs minus the outputs plus any sort of reaction that might be happening. So we might have some sort of rate of growth or rate of decay. And if we add all of those pieces up, maybe there's multiple rates, probably not, especially not in this class. Maybe there's multiple inputs or outputs, no problem. All we do is put all that together and find some value for our accumulation, our net accumulation in that volume. So we can take a very simple example and imagine a swimming pool for a moment. Let's say it's empty and you have a hose leading into it. And we're not going to worry about any concentrations. We're just going to do a mass balance on the water itself. So you turn on the hose and you have an accumulation of water for some time, right? Because the swimming pool is designed to hold water up until it's full, right? And so for a long time, you have an accumulation, and therefore we would say this is not a system at steady state because there is something accumulating. Then, once it gets to the top, the swimming pool probably has some sort of drains or overflows and some place for the water to go when the water is getting too high. Then you have the same amount of water entering and leaving at the same time, and we've very likely reached a steady state. There is water there, and there's water coming in and going out, but we're no longer accumulating water. So that's the accumulation that we're talking about. And so a lot of systems, we want to find a steady state to understand how the system is operating. It's just the math is a lot easier. We don't have to do so much calculus if we're at steady state. So a lot of times we're going to design a system to be continuously flowing and reach a steady state where we're removing stuff over time, and we're happily removing that stuff over time, and we don't have accumulation. It's not always the case, but many times we will have an accumulation rate of 0, but that doesn't mean there's not inputs and outputs or reactions. It just means that we're no longer accumulating, the simple case being water, but typically something in the water. Maybe the amount of waste product. Let's say there's a waste sugar coming from sugarcane processing. So there's a bunch of glucose, sucrose, whatever. We'll just say glucose for now. Coming in the water, and we want to remove it so we're not sending that all out into the river. So we have some biological process consuming a bunch of glucose. We have a continuous feed and a continuous output, and we've lowered that output by having a reaction continuously happening. We could reach a steady state in our system where it does cause a lowering, but we're no longer lowering further or gaining higher. So the accumulation is 0. We've just reached a spot where the reaction happens and it lowers the stuff, but the amount that's actually in there at any given time can be 0. The change in the amount in there could be 0. So it's not about how much is in there, it's about whether or not we have a change. So we will often have a case where we say 0 equals what's coming in, and which is often some flow rate times some concentration initial. I'll write it at C0 or C0. So we might write this as a system where we say V in the volume of the reactor dc dt equals 0, which equals, so that's the accumulation term in the volume, equals what's coming in, and we can write that as the flow rate coming in times the concentration coming in, minus the output, which is usually, if we just have one coming in and one going out, and nothing funny happening about with the water, then it should be the same flow rate, right? Because whatever's coming into this box needs to be the same amount of water going out at least. So we have Q again times some C final. I'll just write it as C. So Q times C plus whatever reactions might be happening. So here, we're going to come back to this later. I'm just going to say the rate of growth and a minus rate of decay in that volume. So that's kind of the scheme of any mass balance that we're going to be dealing with. Of course, we might have something a little different happen, maybe 2 inputs or maybe 2 outputs. So there are ways we can adapt or change, but this is the basics of it. So this is the type of mass balance we'll do. And what you see here is if we're at steady state, we have a nice 0 on the other side that we can shift things around and solve. If we're not at steady state, then we have a differential that we might need to deal with. Okay, so many times we will work with steady state systems, and then we don't have to deal with so much calculus, right? There are cases like a batch reactor. It's quite simple. There's no inputs or outputs, but that also means if there's a reaction, we're not at steady state. So we'll do some simple calculus for batch reactors. Okay, we'll get there. Just this is the groundworks for any mass balance. We're looking at that accumulation, positive or negative, of something in our reactor in question. Okay, so let's give you an example. It's a nice and simple one. We have no reaction here, and I'll explain that as we read. It's from our book. We have 2 polluted streams. It says a stream flowing at 10 cubic meters per second has a tributary feeding into it with a flow of 5 cubic meters per second. The stream's concentration of chloride upstream of the junction is 20 milligrams per liter, and the tributary chloride concentration is 40 milligrams per liter. Treating the chloride as a conservative substance, that's their key word to say it's not reacting. So there's no reaction. and assuming complete mixing of the two streams, find the downstream chloride concentration. Now, you can probably do this just with your intuition. But what I want you to do is take this mass balance approach and set it up in that manner. Okay? We can also assume, if it didn't say it, that these concentrations have been coming in for some time and we've reached some steady state where nothing, like we didn't just suddenly add this tributary a moment ago, right? Something like that could change it, something that is relevant to the timing. So draw it up and solve this using a mass balance approach. All right, how are you feeling about the problem? Okay, so hopefully you set up a mass balance something like this, where you said Okay, accumulation is the inputs minus the outputs, and we didn't have any reactions. So then you can find two different inputs, right? So the Q from the stream and the Q from this waste tributary thing. I think they've labeled it as QW. So you can say each one of those has a concentration, so you could set it up as two inputs. So 0 equals what's coming in from the stream plus what's coming in from the tributary, the waste, minus what's going out, which is this mixture. So they label that QM-CM. Does that make sense? Good on that? Okay. And of course, they said no reaction, so we're keeping that side simple, although really we will be able to work with those. It's not that complicated. It's just more terms over there. Then we're left with QM and CM as the only unknowns right now, and even the little figure shows us that. Here and here. Now we can figure out QM quite simply by recognizing that there's no other sources of water flowing through the system, so it must be the sum of the two inputs, right? So QM should be QS plus QW, right? And that should be safe to assume. That means that should be 15 cubic meters per second. And then from here, what we're left with is these two in the middle, or excuse me, these two inputs equal to the output. So with no reactions, it's really just inputs equals outputs. And that's what I was telling you earlier. You could probably just use your intuition and skip the whole mass balance stuff. You would probably figure that out and do the mass balance without thinking about it. But I wanted you to think through the mass balance process, because once we add reactions, or if it gets complicated in other ways, it's really helpful to use this approach. Okay, so that means we can set, and I'm a little out of space. I think I probably have, yeah. So we have, I'm just going to go ahead and put the QM, CM over here on the left. So QM, we said, was 15 cubic meters per second times some CM value was equal to the inputs, because I'm just shifting that, I'm just adding that to both sides, right? So we had this equation, and I'm adding QM, CM to both sides. So we had 10 cubic meters per second times 20 milligrams chloride per liter, plus this 5 cubic meters per second times 40 milligrams per liter. Now, you might be thinking to yourself, oh no, we already have to do this chemistry, unit conversions, what does chloride weigh, and how do I do that? Well, take a step back and think about this, because you actually don't need that for this particular case. We are answering in milligrams of chloride per liter, and we are given milligrams per chloride per liter. We weren't told anything about any reactions or any chemistry taking place that was important. And we can actually look at our units and say, we need an answer. I don't know if the problem really asked for it, but just asks for the downstream chloride concentration. Oops, did I just erase all that? I did. Sorry about that. I guess I'll write it again. What we're asking for here is this, and it should be fine to do in milligrams per liter. So as we solve our system then, we'll notice that all the units will cancel, because we have cubic meters per second on both sides, and we'll just be left with milligrams per liter. So when we take the 15 cubic meters per second times the unknown CM that we're going to solve for, we can end up dividing units of cubic meters per second from both sides. All right, so real quick, this was 10 cubic meters per second times 20 milligrams per liter plus 5 cubic meters per second times 40. Turns out that 10 times 20 is the same as 5 times 40, and that both are 200, so we'll say CM is equal to 400, and the units here would be cubic meters per second times milligrams per liter. and divide all that by 15 cubic meters per second. So answer should be 400 divided by 15, and the units that will be remaining are cubic meters per milligrams per liter. Anybody have that answer for me? 400 divided by 15? 26.66. Thank you. Yeah, good enough. Okay, so that should be your answer. Is that what you got? Great. Make sense? So it's like a word problem, right? You could have just done this without any special training on mass balances, right? It's like that level of a problem, you can actually just intuit. What's going to change is when we add in some other components. And sure, maybe you could intuit all of that, but a nice streamlined way that your intuition would end up bringing you is this accumulation rate concept. So that's where we're going with that. All right, I think that's probably enough for today. So next time we'll get into reactions in the reactors themselves, how do we model those, and a little discussion about reactors. So enjoy the weekend and Labor Day.